Welcome to the Explainer. So today we're diving into a real mystery, and it's happening right beneath our feet. We're looking at the absolutely incredible phenomenon of why seeds sleep. I mean, we completely rely on seeds for human and animal nutrition, right? They're totally vital to plant life cycles. But sometimes these tiny packages of life decide to just hit a biological snooze button and wait. It's a massive puzzle that pits nature's wild survival instincts against the super urgent demands of human agriculture, and we are going to unlock exactly how it works. Which brings us to a really fascinating question. Why do perfectly healthy seeds absolutely refuse to grow? Just imagine you plant a seed. You give it the perfect amount of moisture, the ideal temperature, exactly the right amount of light. The stage is totally set for life to begin. And yet, some seeds just stay asleep. They sit there, completely viable but totally inactive, just refusing to sprout. Why is that? To figure this out, we've got a 5-part lock and key investigation. We'll quickly cover the sleeping seed mystery, survival superpower or farming foe, biological causes of seed dormancy, breaking the armor with scarification, and finally, internal clocks, stratification, and priming. All right, Section 1, the sleeping seed mystery. Let's establish exactly what this suspended growth actually looks like. The scientific term for this is seed dormancy. Basically, it's defined as when a seed fails to germinate, even under totally favorable environmental conditions. We're talking plenty of moisture, perfect temperatures, good light. And it's absolutely crucial to understand that this is not a dead seed. It's a highly evolved physiological phenomenon, which is actually way more common in wild plants than in our crop plants, where active growth is just temporarily suspended. Now, this is where it gets super interesting because the mystery really splits into 2 different types. You have to ask, is the environment wrong or is the seed literally locking itself from the inside? First, there's imposed dormancy, which is also known as quiescence. This is simply a seed waiting out bad weather, unfavorable external environmental conditions. But innate dormancy, or rest, that is the real puzzle. This is caused by the internal physiological conditions of the seed itself. It has literally everything it needs, but it's internally locked down. Which brings us to Section 2, survival superpower or farming foe. Why does this internal lock even exist? Well, there's a massive clash here between nature's goals and human goals. In nature, dormancy is a brilliant evolutionary armor. Think about small seeds with really hard, impermeable coats, like guava, for example. They can survive being eaten and passed entirely through the digestive tracts of birds. It's basically nature's gritty, frequent flyer program, right? It lets them germinate miles away. It creates long-term soil seed banks to survive brutal droughts. But look at the consequences in agriculture. For farmers, this creates non-uniform seed beds, it drastically reduces overall crop yield, and it honestly just wastes the seeds they consumed for sowing. So, the big takeaway here, nature's brilliant survival lock is honestly a farmer's biggest puzzle. The exact same mechanism that keeps a wild plant alive through a really harsh winter or a dry summer is exactly what frustrates an agricultural system that needs immediate, predictable, uniform growth. Okay, let's jump into Section 3, biological causes of seed dormancy. Time to investigate these specific locks. So if we look at the actual biology, there are basically 3 main culprits at play. First, we have seed coat-induced dormancy. This is where the seed develops this tough, totally impermeable protective barrier while it's ripening, and it literally blocks water and oxygen or just mechanically resists expanding. Second, there's embryo-induced. This means the baby plant inside is either rudimentary, immature, or it specifically needs a chilling period before it can grow. And third, inhibitor-induced. This is wild. There are literal chemical brake pads inside the seed or the fruit pulp that physically prevent germination until they're washed away. And within that embryo-induced category, we find this amazing thing called photoblastic seeds. These are seeds that literally require specific light wavelengths just to wake up. Our source material points to a great example, Lactuca sativa. It's actually stimulated to germinate by red light at exactly 660 nanometers. But get this, its germination is completely inhibited by far red light. The seed acts like a highly sophisticated light sensor. Talk about tough locks. Amaranthus seeds? They can literally hang out in the soil for up to an astonishing 30 years as long as they stay moist. No way, right? We also see plants engaging in literal chemical warfare. Seeds will pack themselves with phenolics, alkaloids, and even cyanide-releasing compounds just to stop themselves from germinating too early. And my personal favorite, desert plant inhibitors. These seeds mathematically wait until a rainstorm is heavy enough to physically dissolve and wash out the chemical inhibitors. That guarantees the plant only sprouts when there's actually enough water to survive. So how on earth do we beat this? Section 4. Breaking the armor with scarification. Let's look at the physical keys. The magic word here is scarification. Because a really tough seed coat completely prevents water entry, we use scarification to physically alter or, well, intentionally damage that seed coat. We basically have to scratch or break past that waterproof, airtight armor so oxygen and water can finally get inside to the embryo. On a massive industrial scale, this gets pretty intensely physical. Farmers will literally throw seeds into giant tumbling drums lined with sandpaper, or even use concrete mixers filled with sand or gravel. It's basically an extreme exfoliation routine for seeds. They're vigorously shaken and rubbed. But the real trick is steps 3 and 4. The gravel has to be a different size so you can actually separate it later, and you absolutely must stop before you over-scarify. If you rub too hard, you destroy the fragile embryo inside. It's a very delicate balance of destruction. And if sandpaper doesn't cut it, we bring out the heavy artillery. Chemical scarification. This brilliantly illustrates how extreme agriculture can get. We use concentrated sulfuric or hydrochloric acid. You place a limited batch of seeds in a glass container, and you never do more than 10 kilograms at a time to strictly avoid overheating. Then you mix 1 part seed to 2 parts acid. You literally let the acid melt away the thick, impermeable outer layers of the seed coat before washing them off. It sounds totally extreme, right? But sometimes a stubborn seed literally just needs a good scratch against a rock. Or, a highly supervised, concentrated acid bath to finally wake up and allow water to enter. But what if the lock is on the inside? That's Section 5, internal clocks, stratification, and priming. If a seed has an immature embryo or internal physiological rest, scratching the outside won't do a thing. Instead, we use stratification. This is defined as keeping seeds in moist, aerated conditions at very specific temperatures for weeks or even months. What this does is it breaks physiological dormancy by literally tricking the seed's internal clock into thinking winter has passed. That causes a shift in internal hormones, which triggers growth. So how do we pull off this biological heist? Well, you basically play Mother Nature. You start by soaking the seeds in 3 to 5 degrees Celsius water for 48 hours. Then you mix them with a moist medium, like sand or peat, using 2 to 4 times the volume of the seeds themselves. Finally, you chill that entire mixture in a cold environment for a specific resting period. You are literally building a fake winter. And in modern farming, we take it even further with advanced keys. We use growth regulators, directly applying hormones like gibberellins to counter the seed's natural inhibitors. We also use priming treatments. There's hydropriming, where we just soak seeds in water, but also osmopriming, which is fascinating. By soaking seeds in low water potential solutions like sodium chloride or PEG 6000, we can actually enhance germination metabolism under severe stress conditions. This is a game changer for helping crops like tomatoes sprout in highly saline soils. So why do we go to all this trouble with acids, fake winters, and chemical priming? Simple. It completely bypasses dormancy. Pre-sowing seed priming ensures rapid, uniform germination, it totally enhances overall seedling vigor, and guarantees those high crop yields that modern agriculture absolutely depends on. It solves the farmer's biggest headache. We've really gone from nature's incredible, stubborn survival mechanics, seeds that are literally willing to wait 30 years in the dirt, to the masterful and sometimes extreme keys of human ingenuity, perfectly designed to command life to begin on our exact schedule. But I want to leave you with this final thought. Seed dormancy evolved in response to very precise environmental cues, right? The exact chill of a winter, the specific volume of a spring rain. As climate change dramatically shifts our weather patterns and scrambles these environmental signals, how is nature going to adapt its dormant locks? And maybe more importantly, as the environment changes all around us, will our agricultural keys still fit? Thanks so much for exploring the amazing science of seed dormancy with me today. Catch you next time.